Oblique collision of a body with a wall. Oblique collision of a body with a wall and with a vertical wall and force exerted by the body on the wall. Force exerted by the body on the wall. This is the vertical wall y1 and y2. y1, y2 is the vertical wall with which a body will collide. y1, y2 is the vertical wall, and we can denote the initial direction of motion of the body and final direction of motion of the body after the elastic collision. We can denote the initial direction. This is the initial direction of motion of the body before the elastic collision, and the body was moving with an initial linear momentum Pi equal mv, and the body collides with the wall at the point O with an initial linear momentum Pi equal mv, and initially the body was moving along the direction AO, collides with the wall at the point O, and after the elastic collision the body will be reflected along the direction OB with the final linear momentum mv, such that velocity remains constant or speed of the body remains constant. In this case, speed remains constant. Here m is the mass of the body which will be traveling towards the wall with the initial velocity v. V is the initial velocity of the body traveling along AO towards the wall obliquely, and the body is traveling towards the wall with an initial velocity Pi equal mv, and the body collides the wall with at an angle theta with the normal, and after the elastic collision the body will be moving with final linear momentum Pf equal mv at an angle theta with the normal at the point of incidence O. The normal can be extended up to negative x-axis or up to x prime. The normal at the point O or perpendicular at the point O on the wall can be extended up to x prime, and this is negative x-axis. This is negative x-axis, that is x prime. And also we can denote the direction along which the initial linear momentum of the body extended in forward direction is extended in forward direction. So this is the direction along which the initial linear momentum Pi equal mv is extended, and this angle will be theta, that means vertically opposite angle, and Pi is equal to mv along this direction is the initial linear momentum of the body extended in forward direction, assuming that there is no vertical wall y1, y2. Assuming that there is no vertical wall y1, y2. Here along OC, linear momentum of the body is Pi equal mv, and that is what initial linear momentum of the body extended in forward direction OC, extended in forward direction OC. In initial direction of motion of the body is along AO, and the linear momentum of the body is extended up to the point C. Now we can denote y-axis or vertical axis, and also we can extend the normal up to x-axis. Towards right we can draw or denote x-axis. We can denote x-axis. So this is the diagram. The rectangular component of initial linear momentum extended in forward direction is Pix equal mv cos theta, which is directed along x-axis, and other rectangular component of initial linear momentum is Piy, which is mv sin theta. Pix equal mb cos theta is directed along x-axis, and Pif, which is equal to mb sin theta, is along y-axis. Final linear momentum Pf can be resolved into two rectangular components. The horizontal rectangular component of final linear momentum Pf is what Pfx is equal to mv cos theta along negative x-axis, and the vertical component of this final linear momentum along y-axis is Pfy. Along y-axis, the vertical component of final linear momentum Pf equal mv is Pfy is equal to mv sin theta. Pfy is equal mv sin theta. So Pfy equal mv sin theta is along positive y-axis. Positive y-axis. Let a body of mass m moving with an initial velocity v collides with a vertical wall y1 y2 at an angle theta that is obliquely. The body collides with the vertical wall obliquely, and the body will be moving with the same velocity, with the same speed or velocity v along the direction OB at the same angle theta with the normal at the point of incidence O after the elastic collision. The initial linear momentum, that is mv, of the body, that is pi equal mv of the body traveling along the direction AO towards the vertical wall, will be y1 y2 is extended in forward direction, that is along OC, that is at an angle theta with the horizontal axis or x-axis, is resolved into two rectangular components. Here Pix equal mb cos theta is the rectangular component of linear momentum mv, which is directed along x-axis, and another rectangular component of initial linear momentum along y-axis is Pix, which is equal to mv sin theta. The two rectangular components of the initial linear momentum pi equal mv extended in forward direction OC are Pix equal mv cos theta along positive x-axis, and Piy equal mv sin theta along y-axis. Also, the two rectangular components of the final linear momentum of the body along OB are given by Pfx equal mb cos theta, which is along negative x-axis, and Pfy is equal mb sin theta along positive y-axis. the linear momentum of the body does not change in vertical direction. That means the linear momentum of the body does not change along y-axis, but it changes along x-axis. It changes along x-axis. That means the linear momentum of the body changes in horizontal direction. The change in linear momentum of the body along x-axis or in horizontal direction or towards right. Change in linear momentum of the body along y-axis, along x-axis, or that is along positive x-axis due to the elastic collision of the body with the vertical wall is given by delta px vector equal pfx vector minus vector pfx minus vector pix. Pfx is the final linear momentum along negative y-axis, which is mb cos theta under bracket minus I cap minus mb cos theta I cap. mb cos theta I cap. mb cos theta under bracket minus I cap minus mb cos theta I cap, as the final linear momentum is along negative x-axis. That's why vector pfx is equal to mod pfx under bracket minus I cap, because I cap is the unit vector along positive x-axis, and minus I cap is the unit vector along negative x-axis, and the final linear momentum, rectangular component of final linear momentum is along negative x-axis. That's how you can write mb cos theta under bracket minus I cap. So finally it should be my delta vector px is equal minus 2mv cos theta I cap. Delta vector px is equal to minus 2mv cos theta I cap, and here y1 y2 is the vertical wall. We can denote I cap along positive x-axis and minus I cap along negative x-axis. Delta vector px is equal minus 2mb cos theta I cap is the change in linear momentum of the body. Change in linear momentum of the body along x-axis. Hence, change in linear momentum of the body along negative x-axis is minus 2mv cos theta I cap. Negative sign in that equation indicates that this change in linear momentum of the body occurs along negative x-axis. This negative sign indicates that this change in linear momentum occurs along negative x-axis. Therefore, the change in linear momentum imparted to the wall, of the body imparted to the vertical wall, y1 y2 at right angle with respect to the wall. At right angle to it means at right angle to the wall is given by delta vector px prime, delta vector px prime. Delta vector px prime equal minus delta px. We can denote the vertical wall, that means y1 y2 is the vertical wall. We can draw a perpendicular to this vertical wall, and this is negative x-axis, and this is the vertical wall. This is the vertical wall, and we can denote positive x-axis towards right, positive x-axis. This is the positive x-axis towards right with respect to the vertical wall. In this case, change in linear momentum of the body along negative x-axis is what? Minus delta px is equal to minus 2mv cos theta I cap. Minus 2mv cos theta I cap. And in this case, change in linear momentum, that is delta px prime, with delta px prime which is imparted to the wall by the body is delta px prime, and delta vector px is the change in linear momentum vector, change in linear momentum vector of the body along negative x-axis. And delta px prime, delta vector px prime is the change in linear momentum vector, change in linear momentum vector. Delta px prime vector is the change in linear momentum vector imparted to the wall along positive x-axis, imparted to the wall along positive x-axis, or comma delta vector px prime is equal minus under bracket minus 2mb cos theta I cap. Therefore, delta vector px prime is equal to mv cos theta I cap, 2mv cos theta I cap. Delta vector px prime equal to mv cos theta I cap. This is the change in linear momentum. This is the change in linear momentum of the body. Change in linear momentum imparted to the wall, change in linear momentum imparted to the wall due to the elastic collision of the body with the vertical wall. Delta vector px prime equal to mv cos theta I cap. That is the change in linear momentum imparted to the wall. Therefore, the force vector exerted to the wall, the force vector exerted to the wall, force vector exerted to the vertical wall y1 y2 at right angle to it, is given by vector fx prime is equal to delta vector px prime divided by delta t, delta vector px prime divided by delta t, where delta t is the interval of time during which the body undergoes the elastic collision with the wall. Here vector fx equal 2mv cos theta I cap divided by delta t. Therefore, vector fx prime is equal to mv cos theta, 2mv cos theta divided by delta t, bracket closed, I cap. That is, vector fx prime is equal to 2mv cos theta delta t divided by I cap, and here this force vector, that means vector fx prime acts towards right along x-axis and perpendicular to the vertical wall. Therefore, fx prime equal mod vector fx prime equal mod vector fx prime. That is, magnitude of this force equal mod 2mv cos theta divided by delta t I cap equal to mv cos theta divided by delta t mod I cap, where I cap is the unit vector along x-axis, 2mv cos theta divided by delta t. Since mod I cap is equal to 1, or magnitude of unit vector along x-axis is unity. Therefore, we get fx prime equal to mv cos theta. Fx prime equal to mv cos theta divided by delta t. Fx prime equal to mb cos theta divided by delta t, which is the force exerted to the vertical wall y1 y2, force exerted to the vertical wall y1 y2 due to the elastic collision of the body with the wall, due to the elastic collision of the body with the vertical wall, fx prime equal to mb cos theta divided by delta t. And this force acts at right angle to the vertical wall. This force acts at right angle to the vertical wall, that is, it acts along x-axis, or that is, it acts along positive x-axis. This is the vertical wall in the diagram. A body having mass m will be traveling with a speed v, and the body has mass m. We can draw a perpendicular at the point of incidence, the perpendicular at the point at which the body collides with the wall. That means this perpendicular can be assumed as x-axis, and the body is traveling towards the wall with constant speed v. And in that case, the force exerted to this vertical wall by the ball due to its elastic collision is equal to fx prime equal to mb cos theta divided by delta t, and this force fx prime acts along positive x-axis at right angle to the vertical wall. Finally, we get the expression of force exerted to the vertical wall, which is fx prime equal to mb cos theta divided by delta t.